also related to some kind of, let's say, generalization or modification of the deformed exponential families. So, actually, getting back to the main motivation, 2013, we have proposed a paper, let's say, in a more general model, or a more general model of probability distributions called, I have called it at that time like 5 families. But indeed, it's a kind of deformed exponential family. And the point is, if that family or that kind of distribution is written in a way that it's dependent on a function phi, and also on some normalizing functions like the C1, C of U, and U0 function as well. So that normalizing function, of course, is necessary to make that family to belong or to be inserted in a given manifold. And sorry, okay, sorry. Then at that time we didn't pay much attention about that normalizing function, but after some time we realized that it plays an important role in the definition of the function and then how the probability density function behaves. And so this work is one step forward to understand a little bit better about that behavior. So still on that direction, a previous work, we have also discussed some conditions specifically for the delta 2 condition about those families, and somehow they behave in that sense, if that kind of normalizing function, how it works for those cases of fulfilling that delta 2 condition. But in this case, in this paper actually, we are dealing in a little bit different way. So let's going back again to the definition of those phi functions that we have proposed at that time. So they need to fulfill some conditions, so A1 up to A3. So not many complicated ones, but it needs to be convex and then injective. So the limit when the argument goes to infinity and minus infinity should be limited to 0 for the minus infinity, and grows up to infinity. And more important, we should have a limited, a bounded function for that case, for the phi of the function for a given lambda u0. Again, the u0 appears as an important role. For such which the function should have the integral equals 1. So being a probability function. This is not limited, but allows not much degrees of freedom to make the analysis. So we have worked a little bit with a slightly different condition, which is A3 prime now. And the only difference is almost the same about the integral of the function for any lambda positive. It should be a limited, a bounded value for that integral. But instead of having the integral of the function itself equals to 1, it should be only limited. So this is, I have proven that it's an equivalent situation, the equivalent condition. And we start from that and say, okay, what if we have functions that do not respect those, at least they respect part of the conditions from A1 and A2, and do not respect one of those, or at least the A3 or A3 prime. So here, an example. So if the phi function is given like that, so it respects A1 and A2, but do not respect the A3 or A3 prime. So the integral is going to infinity actually. So in that case, what happens to our normalizing function, and what does brings as a new distribution function? So these are some definitions actually. So the phi family is the whole set of all possible distributions on the boundary of that, actually on the set of those arguments. So again, we are just writing up there. So the function has the argument c, u, and the normalizing psi u in u0. Okay. And the point is, one thing is what happens in the boundary, actually on the very far part of the domain of the function. So that's the question that we would like to answer in this paper. So for a specific or for a given phi function satisfying a1 and a2 but not a3, okay, or its equivalent a3 prime. So it is possible to know whether that function, the normalizing one, converges or not to a finite value in order to make that integral of the function still be a defined probability one. Okay, so as alpha grows to 1, increases, so it's still going to be a limited, a bounded value. So for the I forgot to mention maybe that let's say the more not realistic, but the more proper way of defining is based on the Musilek-Orlik spaces. So the function, the phi functions should rely on those spaces. And again, in that conditions, if the function, which is now the phi function as we call it, satisfies the delta 2 conditions, we may write that equation that for a given 2u psi of a function phi, for 2u is lower or equal than a constant multiplied by the function in a given point u, belonging to a given function. So, on the other hand, if that function phi of c, which is our distribution, does not satisfy that delta 2 condition, the boundary, or at least the existence of points in the boundary of the function, is non-empty. So that's an important point. And we say, in that case, that if the argument or the points belong to that boundary, it's a delta, the differential of that calligraphic B, belongs to that, if and only if the integral is limited, and more than that, the integral for a given phi of c plus lambda u goes to infinity, at least it's infinity, for a given lambda greater than 1. For lambdas smaller than 1, we can achieve bounded integrals for that part. Okay. So let's now consider that the psi does not satisfy the delta 2 condition. What does it happen? What does it imply? But that happens, and if the phi function satisfies the condition a3 prime, which is still having the limited, a bounded part for both cases, both integrals are limited, but not equal to 1. Okay? We have the following conditions. The first one, the integral is bounded, but the normalizing function converges to a beta parameter, which is, it can be also unbounded. It can grows up to infinity as long as alpha grows to 1, which is the argument of the function. And the other condition is, in the case that the integral is equals to infinity, so the normalizing functions also grows to infinity. So we are having two different points if, in the case that we are not satisfying the delta 2 condition. Sorry. Okay, so this is the equivalent of that situation, existence condition, for alpha greater than 0 and for given constants lambdas, is that we can write for a given function u, actually for values of u greater than a function of t, can be represented in that boxed equation, which is showing that for the alpha parameter, it can affect for the given u0 on the other side. So it's still bounded in some sense, but the u0 is going to play an important role as well. In that case, the condition A3 prime is not satisfied if and only if there exists the function such that lambda bar times u0 inside the integral. We can show here. Okay. Here, it's still also bounded. Okay, for any positive lambda bar. In the case this condition A3 prime is not satisfied, we are able, actually this is the main result of the paper, we can find a sequence of lambdas that allow to have those limited to bounded integrals on that. So these are the forms, so we have some constant part of the sequences, and then the sequences are bounded also for the 2 over minus n for n greater or equal than 1. And this is what's the intermediary result that is ends up to this proof. So all those aspects of the conditions about the normalizing functions and how they behave, the impact of that normalizing function on the boundary of the distributions, it's summarized in, let's say, that proposition as the main result of the paper. So in the case that the condition is not satisfied, it means that we are working with functions like that previous one. Let me going back to show again. Oops. Okay, in that case, so that function does not satisfy the A3. Okay, it's not bounded anymore. So in that case, we should have actually there we can prove, actually it's proven in the paper, that there exists u over lying on the boundary that turns out to make the integral equals to infinity as long as alpha grows to 1. So this tells us that we can, let's say, generalize a little bit further what that deformed exponential, kind of deformed exponential, which is one among the others that we can write, that provides a wider class of distribution probabilities. So these are basically the summary what I have mentioned. So the final bullet over there. So we conclude that the condition A3 prime affects the behavior of the normalizing function. So whether or not we are considering to be limited the integral of the function over the domain, so it's going to affect very much what happens in the boundary. And so this is important if we are, for example, considering path connecting distributions, because this is going to be affecting more and more the boundaries of those. And finally, as future works, also, as I said, we are still considering the fulfilling two of those conditions, being convex and injective, and the limit of the functions to certain aspects. So we are trying to relax one of those conditions in order to make the function not necessarily injective anymore. So what happens? Is it still possible to define a new or more general distribution in that case? And also, in a different aspect of different direction, sorry. So we could, to investigate, for example, in the case that the statistical manifold being equipped with a C infinity Banach manifold structure. So can we use a phi function in that case, whether, or in the case that the condition A3 is not satisfied also? So again, it's just a way of relaxing the conditions that they need to fulfill in order to go to verify, to specify the existence conditions and so on and so forth. So, thank you.
Okay, so the paper is open for discussion. We have 5 minutes for discussion.
Sharp.
Any questions? No, I really have questions. So this setting of the your function, free function, this is used in the non-parametric density.
Yes,
function, right?
yes,
So,
absolutely.
yes.
No parametric.
Can you say anything about like what relevance does it bear for the parametric models?
We have some work at some still, let's say, initial works on that part. The main point is that we need to change a little bit the definition or the support of those functions, because in the sense of the Musi-like Orliks, we need to, let's say, constrain a little bit more on those. So, as far as we already, let's say, investigated so far, we can extend somehow some of the results to a parametric aspect. It's, let's say, simplify some steps, but of course we need to verify if the conditions, the existence ones, are more relevant or not. In our case, in this specific one, for the parametric one, we went to a, let's say, generalization of the Renyi entropy based on those definitions, because we can also define based on those phi functions of phi divergence and so on. So we used those for a parametric case where we can parameterize for a given pair of distributions, for example.
So a question may be related, but it was on your earlier work of your group.
Okay.
There was something using this formulation to derive some divergence functions or cross entropy functions. So I remember there's a form of a divergence function associated with that. Can you comment on that in relation to the general, like the rotor embedding and so on?
Yes. Actually, one of these works is related to that part, because I think that our model, our divergence is related to the rotor apart from a scaling factor or something. So the rotor is more general than our case in some sense, but the writing is a little bit different. So one of our previous work was trying to make some kind of correspondence of those models. And now we are aiming to, let's say, go in some directions that providing, let's say, is there any possible condition that we may, like, may be a general model that could, let's say, cover from rho tau up to other models in order to make a more wider class of the divergences. So this is an active also research line that we are pursuing so far at this moment.
So just also mention this in class, because I will try to understand, try to link with the rotor formulation that I'm trying to do. So the divergence seemed to be that of a type 2 kind, type 2 gauge, but I'm not absolutely certain about this. Maybe because the type 2 gauge is associated with this condition of essential normalization condition of the probability function. So I don't know whether that's implicitly used somewhere to derive this or something.
Yeah. From your presentation, I had this same, let's say, feeling, but I need to verify some steps in order to, let's say, make a more clear statement on that. But it seems so. It seems to be on type 2. So it's different. Of course, we could, let's say, put some constraints about those phi functions in order to match with those rho and tau choices of the dual and so on. But it seems to be, let's say, so far a promising way to go further and make some, let's say, some convergence on those topics.
Okay, any more questions? Okay, no. Thank you very much. Thank you.